talks today, and we will have reading week next week, so no talk next week. So this will be the last one before the reading will resume after reading week. So today we'll have two excellent talks. The first one will be given by Alyssa Atkinson. And Alyssa is an undergraduate student working with one and March here, and particularly she is working in the radio lab here with Nina. Some of you might know, and so today she's going to talk about the project she has been working on. I also want to highlight that this is a Dunlap seed funding supported project, so it's nice to hear some of the progress on this. So please take it away, Alyssa.
Thank you. My name is Alyssa. She introduced me. So yeah, I'm going to be talking about the results of some funding that was received to install a new modern atomic clock system at the Algonquin Radio Observatory. And the purpose of installing this was to restore its very long baseline interferometry capabilities. So also talk about what that means and the results of the funding. So ARO, I'm just going to call it ARO. Is an observatory about 6 hours away from Toronto, and it has this spherical has this conveyor dish that just looks up at the sky, like at one point, and then it has this newly built log periodic dipole array, this array of antennas, which is still in commissioning, and we hope to be able to do VLBI with it at some point soon. So that's one of the reasons why we want to do VLBI with ARO. But we have access to its facilities as UT astronomers. It's owned by a private company, but we are able to go in and test different like new instrumentation and use the data acquisition software to take data, do science. So it's really great observatory, and also it was one of the first two telescopes used to do the very first Very Long Baseline Interferometry, along with a telescope at the ARO, which is actually pretty cool because I'll be talking today largely about the plan for VLBI in terms of the Algonquin Radio Telescope and the CHIME baseline, which is CHIME is at the ARO. So yeah, that's a little fun historical fact. It's very bigger in VLBI. So deeper into exactly what is VLBI, just as in case certain people do stuff that's not radio astronomy. So, and the reason that when you have a telescope, as I'm sure most of us know, the resolution it is dependent on 1 over the aperture of your telescope. Or if you're talking about a radio interferometer, this is analogous to the separation between the stations that you're using. And so the further, basically the bigger the baseline, the further away, the better precision that you get in your images, or if you're localizing things, like the more precisely you can localize things. So that's kind of the motivation for one of the motivations for VLBI, why we want to be able to do VLBI. And the reason that we need good clocks, which is what we got funding for, is clocks. I'll talk about that second. But the reason why is because to use an interferometer, you have to use the delay and the signals arriving at the telescopes to get back out the information that you're trying to be able to actually use them as one telescope together. But unfortunately, this tau, like this geometric tau that depends on the geometry, can be, if your two stations are not perfectly synchronized, in terms of the timing, like the clocks there, then you can attribute some timing delay to the actual geometric delay of your signal, and then that affects your errors in your precision. This particular, there are other delays, for example, spirit delay that can cause problems, but this one actually see the difference. So it's easier to remove, but both the geometric and clock delay have a lunar dependence on frequencies, so you can't really expect to disentangle them, which is why it's important that we have good clocks. And so before I go into more of clocks, I'll quickly take a sidebar to talk about why we want to continue to do very long baseline interferometry at ARO. There are a lot of great observatories that do VLBI and do great VLBI, but ARO is an important part of the overall puzzle. And it's very useful. So one recent successful VLBI experiment you may have heard of from ARO was a fast radio burst localized to its host galaxy using CHIME. And then to do a localization, you need two kind of like outer telescopes far away from it because you have to localize it in both dimensions. And so without CHIME in the ARO, we're able to do lots of localization to the host galaxy, and that was taking advantage of the fact that ARO at that time could do VLBI, which then it broke, and then this is about restarting the ability. And also, being able to do VLBI also supported scintillometry. I'm not for scintillometry, but I talked to some of my scintillometry friends, and they told me that having a precise atomic clock can help. You don't necessarily need a precise atomic clock, but you need a clock that works to a specific precision, otherwise you can't even be like needed for scintillometry. So it also is relevant for that. And also, like I mentioned, a lot of testing goes on in ARO, testing VLBI methods and instrumentation. And this is not an exhaustive list of all the VLBI ever done in ARO, it's just kind of why it's still in the game kind of thing. Okay, so now we'll get to the clock. So at ARO, there was a hydrogen maser, which is a very precise atomic clock, which kept time very well at ARO. And the way that it worked, when it was still working, is that you would get a clock, a master clock, and knows what time it is via GPS at the beginning of your observation. And then this master clock, it doesn't necessarily know that it's like, I don't know, June 10th, 2022, but it knows how to count like tiny amounts of seconds very precisely. And so that's how observations were taken at ARO. The important thing here is that we used to rely on this maser to keep us a very good 10 megahertz signal. So not only did we want it to be good on very tiny time scales, but we wanted it to be able to accurately count 10 megahertz over and over again. And so we used it as like the only clock for the whole observation, other than like, the first timestamp given by the GPS. Unfortunately, it began to malfunction at some point. We don't know exactly when, I think around this time. And so we say it lost its frequency stability. It was no longer able to tell us to keep that steady signal for us to tell us what time it is and do VLBI, which is a problem because then we didn't have any working clock setup to do VLBI. And so what this is showing here is this is called Allen deviation, and it's just the way to think about it is it's just the measurement of how stable the clock is on a certain time scale. So this is like 10 to the 1 second, 10 to 4 seconds. So lower is that. So the maser was not doing well, as you can see. These clocks here, as I tried, they have a GPS discipline crystal oscillator, so that keeps the 10 megahertz for you, but then the maser can correct for that GPS crystal oscillator on very small time scales because it's still better on smaller time scales. So they have an atomic clock system going on there. And then this black line is KVO, which is one of the CHIME outriggers. And sorry, I should mention CHIME outriggers are, you have CHIME, you have DRIO, and you have these outriggers that are coming to life that are long baseline away from CHIME to localize stereo bursts. So anyway, try. So they do not have a maser because masers are hard to come by because they're very expensive and rare and stuff. Video atomic clock, which almost performs as well with that combined crystal oscillator and GPS setup that I was talking about. They have a CHIME maser, and so essentially what this is showing is that compared to what they have, and this is not good enough for VLBI, this is time of precision. And so luckily we have these lines at the bottom. And so our proposal, our Nina's proposal, was okay, let's just replicate that setup at ARO. And so that's what the goal was to do. So this is the GPS clock with the crystal oscillator, and then again the repeating clock. The goal is to put those, we did get these and put them at ARO, install them at ARO, and then we want to see how the timing works for VLBI. So this is a plot that has a lot of lines, sorry, but I'll take the attention. So basically, now I have a bunch of plots on ARO. And so this orange line is the laser, but it's being, we're using the GPS signal as our standard 10 megahertz frequency standard, and then correcting it on shorter time scales with the maser. And then this blue line, this light blue line is the rubidium. The same thing with the rubidium. And you actually see, once you get to about here, it's actually better because as the maser is growing, that's another reason we're seeing the behavior of the maser compared to rubidium. But in terms of like the ARO installed performs definitely well enough for the VLBI, since it even overtakes the maser at some point, which could be due to the maser having issues with its frequency stability. So that previous thing that I just showed with the alpha deviation is just kind of, it's a way to quantify like how good is our clock, but it also it can't really test the clock without comparing it to another clock. So my project in the summer was about testing these new clocks, but against the sky. So what I would do is I would take pulsars at CHIME and ARO and use the same pulsar kind of, it almost is like a clock. Well, like basically it pulses a bunch of times, and then that each pulse is like one data point here. So what I would do is I would correlate the two data sets and then extract what we expect the geometric delay to be. So then, and also the fitting for other effects that cause delay. So ideally, what we're seeing here is mostly just like clock timing residuals. And so using pulsars to test if the clocks are actually working. And so this is before the practice. The time steps here are given by the GPS crystal oscillator. And you can see that like it's not super good on short time scale, but luckily we have this correction from the CHIME and ARO. Making that correction, this is like 25 milliseconds to scale, and this is like 10 milliseconds. And there's very, very small like time fluctuations and perform very well in terms of the short time scale timing. The only thing is that the limits are a little bit here. We're not 100% sure if this is yes long-term thing, or this could also be due to not perfectly, like you could have a systematic effect like this for not perfectly correcting for the geometric delay. So that's still something that I'm investigating in my current project. But the kind of the conclusion of my summer project was that the policies work pretty well against the sky. I think I figured out that if there was a calibrator within like 20 minutes of the fast universe, we would be able to localize it to its host galaxy without even correcting for any drifting. But if it was a longer time in between calibrators, we might need to do some correction. But I think that the moral story is that we're able to see what's going on and like correct these things. And so let's just talk about one thing that I'm currently working on that is a little bit more like the specific timing clock stuff, but still sort of related, is the kind of what I was just talking about. Like if you have a fast universe that's like a significant amount of time away from an FRB, how does our new timing clock system behave, and what are the timing residuals? So like this is an example of two crowd pulses that are 2 days away. And so I'm currently working on like referencing these to each other, and not just these two, but multiple, referencing them all to each other, and then like looking at like how much does the clock drift? Is there like how well would we be able to like what would our error budget be if this was an FRB and not a pulsar with a no position? So the overarching conclusion is that we have clocks that can do VLBI at ARO once again, which is great. We can put UFT astronomers can once again like test VLBI, do VLBI science using the Algonquin Radio Observatory. I don't want to stress this enough, but we can actually get there by car. So we can actually like last summer we took physically like antennas to like test them over there. So it's like super great to have a radio observatory like within driving distance. And so we're confident in its restored VLBI capabilities. Also, my goal, what I was just talking about with my project, is using this new system to try to use these log periodic dipole arrays. One, the one that they are body eventually, to try to localize little faster universe, which are right FRBs kind of from the side of trying to be. I can talk more about that if anyone has questions, but I shouldn't get too much into that because it's getting more to the science of logic and all that stuff. But yeah, so we installed new clocks. They seem to be working. We seem to be able to do VLBI again, and that was all thanks to the funding from the FRB funding. Thank you, and also these are some acknowledgements to people who are part of this project. This is not an exhaustive list. A lot of people are part of all this. But yeah, that's all. Thank you.
Maybe I'll start. So you mentioned a little bit at the end, like now that we have this is working, we will then choose ARO or the computer for your science.
Sure. So the CHIME FRB Outriggers campaign is using CHIME, ARO, and then a series of smaller CHIME telescopes built around it to try to localize fast radio bursts to very good precision, which is interesting because if you can localize an FRB to its host galaxy, you might be able to say something about its origin. Or if it's a closer FRB, like if it's one in our galaxy and you localize it with that precision, you might be able to say like, oh, it's coming from Magnetar, which I think, I don't know, there's one FRB that was determined to be coming from Magnetar. I haven't looked into that. The point is, localizing FRBs can lead to very cool science. And so my project is trying to see if we can use these tiny little arrays to do the same thing for side lobe FRBs. Because they have a very, very wide field of view. So if there's a side lobe FRB at CHIME, the outriggers might not see it, but the idea is that hopefully the LPA would see it. And even though it has low sensitivity, since these pulses are so bright, we're talking about really bright FRBs because they have to be seen in like the side beam of CHIME. We want to see if we can do VLBI to localize those. And that would not only be cool because we'd be localizing FRBs, but also like just to be able to know that we can use just a small array to do like this precise science. It's kind of the end goal.
Any other questions?
Specifically, what are the receivers at ARO?
Sorry?
What are the receivers at ARO?
What are the receivers?
Yeah. So what frequencies do they observe at?
Oh, so around CHIME frequency, so like 400 to 800 megahertz. Yeah, I think it's just 400 to 800.
We're installing a new feed. That's the fee I made. So it's for cores to cover the core.
And what is it?
300 to 1500.
Cool.
But that's not working yet.
That would be our
We're
40.
experimenting with this, as she says.
That's 46. So that would be very cool. The 46 meter was like a steerable.
Any other question for Alyssa? Okay, now let's thank Alyssa again. Thank you. So we're gonna do the switch and I'll probably introduce our next speaker. And now we're going to so we become more focusing on the optical.
Waiting for that.